IT361 Module 3 Part 2. In this part, we are going to discuss about independent sets and cliques. First, we can see what is an independent set. A subset S of V is called an independent set of a graph G if no two vertices of S are adjacent in G. And next is a theorem based on the concept of independent set. A set S subset or equal to V, where V indicates the vertex set of G, is an independent set of the graph G if and only if V minus S is a covering of G. We have already discussed about the covering of a graph in the first part of this module. Now we can see how we can prove it. We know by definition S is an independent set of a graph G if and only if no edge of G are both ends in S or equivalently if and only if each edge has at least one end in V minus S. But this is so if and only if V minus S is a covering of a graph G. Hence the theorem. The number of vertices in a maximum independent set of G is called the independence number of G and is denoted by alpha of G. Similarly, the number of vertices in a minimum covering of G is the covering number of G and is denoted by beta of G. Next is about clique. A clique of a simple graph G is a subset S of V such that the graph formulated by S, which is denoted as G of S, is complete. Clearly, S is a clique of graph G if and only if S is an independent set of G, and so the two concepts are complementary. Now we can see what is a Ramsey number. Given any positive integers k and l, there exists a smallest integer denoted by RKL, such that every graph on RKL vertices contains either a clique of k vertices or an independent set of L vertices. For example, it is easy to see that R1L is equal to RKL equal to 1 and R2L equal to L, RK2 equal to K. The numbers RKL are known as the Ramsey numbers. Ramsey's theorem is stated as: for any two integers k greater than or equal to 2 and I greater than or equal to 2, R of k, L less than or equal to R of k, L minus 1 plus R of k minus 1, L. Furthermore, if R of k, L minus 1 and R of k minus 1, L are both even, then strict inequality holds. That means at that time R of k, L will be less than R of k, L minus 1 plus R of k minus 1, L. Now we can see how we can prove it. For that, let G be a graph on R of k, L minus 1 plus R of k minus 1, L vertices, and let a vertex V element of the vertex set of the graph, capital V. We distinguish two cases. The first one is V is non-adjacent to a set S of at least R of k, L minus 1 vertices, or V is adjacent to a set capital T of at least R of k minus 1, L vertices. Note that either case 1 or case 2 must hold because the number of vertices to which V is non-adjacent plus the number of vertices to which V is adjacent is equal to R of k, L minus 1 plus R of k minus 1, L minus 1. In case 1, the graph formulated by the subset of vertices S, which is denoted as G of S, contains either a clique of k vertices or an independent set of L minus 1 vertices, and therefore G of S union singleton set V contains either a clique of k vertices or an independent set of I vertices. Similarly, in case 2, G of T union set V contains either a clique of k vertices or an independent set of L vertices. Since one of case 1 and case 2 must hold, it follows that the graph G contains either a clique of k vertices or an independent set of L vertices. This proves the inequality. Now suppose that R of k comma L minus 1 and R of k minus 1 comma L are both even, and let G be a graph on R of k comma L minus 1 plus R of k minus 1 comma L minus 1 vertices. Since G has an odd number of vertices, it follows that some vertex V is of even degree. In particular, V cannot be adjacent to precisely R of k minus 1 comma L minus 1 vertices. Consequently, either case 1 or case 2 above holds, and therefore G contains either a clique of k vertices or an independent set of L vertices. Thus, R of k comma L less than R of k comma L minus 1 plus R of k minus 1 comma L minus 1. Next is a theorem that we will use in the coming theorem, namely the Toran's theorem. If a simple graph G contains no k m plus 1, then G is degree majorized by some complete M-partite graph H. Moreover, if G has the same degree sequence as H, then G is congruent to H. If G is simple and contains no km plus 1, then edge set of G less than or equal to edge set of T m comma V. Moreover, edge set of G is equal to edge set of T m comma V only if G is isomorphic to T m comma V. That is actually the Toran's theorem. Now we can see how we can prove it. Let G be a simple graph that contains no km plus 1. Then by the previous theorem, G is degree majorized by some complete M-partite graph H. It follows that edge set of G less than or equal to edge set of H, but edge set of H is less than or equal to edge set of T of M comma V. Therefore, edge set of G less than or equal to edge set of T m comma V, proving the first assertion. Suppose now that equality holds in epsilon of G less than or equal to epsilon of T m comma V. Then equality must hold in both edge set of G less than or equal to edge set of H and edge set of H less than or equal to edge set of T m comma V. Since edge set of G is equal to edge set of H and G is degree majorized by H, G must have the same degree sequence as H. Therefore, by the previous theorem, G is isomorphic to H. Also, since edge set of H is equal to edge set of T m comma V, it follows that H is isomorphic to T m comma V. So we conclude that the graph G is isomorphic to T m comma V. Next is Schur's theorem. The statement is, let S1, S2, etc. Sn be any partition of the set of integers 1, 2, etc. up to Rn. Then for some I, the set Si contains 3 integers x, y and z, satisfying the equation x plus y equal to z. Let's have a look at the proof of that theorem. Consider the complete graph whose vertex set is 1, 2, etc. up to Rn. Color the edges of this graph in colors 1, 2 up to n by the rule that the edge uv is assigned color j if and only if modulus of u minus v element of sj. By Ramsey's theorem, where the inequality is given by the equation 7.7, there exists a monochromatic triangle, that is, there are 3 vertices A, B and C such that AB, BC and CA have the same color, say I. Assume without loss of generality that A greater than B greater than C and write x equal to A minus B, y equal to B minus C and z equal to A minus C. Then xyz element of Si and x plus y is equal to z. Hence the theorem. Next is the concept relating to the diameter of a set S. The diameter of a set S of points in the plane is the maximum distance between 2 points of the set S. Now we are going to use the concept of diameter of points in the set S in one of the applications, namely a geometry problem. We shall discuss sets of diameter 1. A set of n points determines nc2 distances between pairs of these points. It is intuitively clear that if n is large, then some of these distances must be small. Therefore, for any d between 0 and 1, we can ask how many pairs of points in a set x1, x2, etc. xn of diameter 1 can be at distance greater than d. Here we shall present a solution to one special case of this problem, namely when d equal to 1 by root 2. The solution to the problem in general is given by the following theorem. If set x1, x2, etc. xn is a set of diameter 1 in the plane, the maximum possible number of pairs of points at distance greater than 1 by root 2 is greatest integer n square by 3. Moreover, for each n, there is a set x1, x2, etc. xn of diameter 1 with exactly n's greatest integer of n square by 3 pairs of points at distance greater than 1 by root 2. Now these are some problems from this topic for your practice. Try to do it by yourself. That's all from this topic. Thank you.